All right, again, I'm George Crump with Storage Switzerland. Next up, I have the privilege of introducing Salil Raje. He heads the data center group for Xilinx, leading a global team of engineering, sales, manufacturing, marketing professionals dedicated to the data center, the fastest growing market for FPGAs. His group helps hyperscalers, enterprise cloud providers, harness intelligent, adaptable infrastructure to improve performance, power efficiency, and operating costs. So please join me in welcoming Salil to the stage.
George. Good afternoon, everyone. This is my very first time at the Flash Memory Summit. Quite excited to be here. I'm actually very impressed by the size and scope of this event. I actually shouldn't be surprised because I know that Flash has disrupted storage industry and, in fact, data centers. Now, here today, I'm going to talk about yet another disruptive technology, and you heard a lot about it today. That's computational storage. And I'm also going to talk about how FPGAs play a role in enabling computational storage. So I've seen a bunch of talks today, and a lot of them were about computational storage. So I'm going to modify the question I was actually going to ask, which is now, how many of you knew about computational storage before you entered the conference? Raise your hands. OK, not that many, actually. How many of you have actually used FPGAs in your applications? Only the Xilinx folks. OK, so whether you know about computational storage or FPGAs, my goal today is to give you a brief overview about computational storage and also talk about how FPGAs can act as adaptable accelerators. You may have heard about FPGAs in the traditional context, but I'm going to talk about how FPGAs can be adaptable accelerators enabling computational storage. And we're also going to talk about how data centers will evolve and how computational storage will play a pivotal role in the new data center architectures. Now, almost all of you here know that SSDs have been a game changer in many ways. I mean, in power, cost, reliability, performance. But the one key metric, the striking metric, has been latency. Moving from HDDs to SSDs, we've seen about 2 orders of magnitude improvement. And as we move towards storage class memories, we'll see another 1 or 2 orders of magnitude of improvement in latency. Now, you would think that with that level of improvement, there would be no issues, no challenges with respect to application performance. However, as SSDs have come into play, NVMe has come into play, we also seen an explosion in unstructured data. And we've seen an explosion in a lot of the new workloads that use some of this unstructured data. Retail analytics, bioinformatics, video, and then machine learning will have an even bigger impact. Now, a lot of these new workloads put a huge load on our storage, networking, and compute resources. And that is why we need acceleration. If you look at it from the standpoint of just storage, there are a lot of these low-level functions, compression, decompression, encryption, and data filtering, that has to act. These have to act on all bytes of data. And that is yet another challenge we see. Now, adding to all of these challenges is the fact that these workloads continue to change, and newer workloads continue to get created. Also, some of these low-level functions, such as the compression, decompression, and so on, also depend on standards that continue to get modified. So if you look at just databases alone, there's a lot of new formats, just a plethora of databases, right? Hadoop, Spark, of course, but then RocksDB, Cassandra, Foundation. If you look at different hyperscalers, they have their own databases. If you look at even compression, which you would think that it's a well-known technology, is also continues to change. Right? We went from gzip, Brotli. Just in this year in OCP, Microsoft introduced yet another compression technology, Zipline. Blockchain also will have a significant impact on encryption. So you can see the workloads are changing, standards are changing, some of these low-level functions have to continue to change. So it's really hard for any fixed architectures, any ASICs and ASSPs, to truly keep up with these changes. So as I said, SSDs have continued to improve, but the performance bottlenecks have not gone away. They have just moved. In a CPU-centric architecture, a lot of these low-level functions have to act on all bytes of data, and this data has to move from SSDs into memory with the compute in the middle. And because CPUs are not optimized for some of these low-level functions, that causes latency and bandwidth issues. So these CPUs are spending all these cycles in these low-level functions, and they should actually be spending all their cycles on workloads that can be monetized. So the obvious answer, of course, is to move the compute close to the storage. And that is exactly computational storage. In computational storage, you move the compute close to the SSDs, and you work on the data in an inner loop with an SSD, improving latency and performance for the low-level application functions so that the higher-level functions can be done in the CPUs, where the CPUs now are freed up to do some of these functions. And this also improves bandwidth. Now, the need and importance of computational storage is well understood, and there are a lot of companies now jumping on the bandwagon. So here at the conference, already there are many companies now working on computational storage. There's also a SNIA working group that is focused on interoperability standards. Xilinx is one of them. Now, of course, as I said, the need and importance of computational storage is well understood. The SNIA working group is working on these. But the key question is, what is the exact approach to address some of these challenges? And that is where FPGAs come in. So FPGAs are not new to the storage industry. We have been used, Xilinx FPGAs specifically have been used for almost a decade in flash controllers. We have also been used in key functions in storage systems such as cache offload, switching connectivity, and data reduction. But the value of FPGAs is even more pronounced when you get to computational storage. Now, for those of you who don't know FPGAs, FPGAs are a configurable architecture that can be optimized for any workload in milliseconds by simply uploading a bit stream. They come with a lot of parallelism. They come in with customized data flows. You can have customized memory hierarchies. So you can rival the performance and latency of an ASIC or an ASSP with an FPGA, but at the same time, keep it software programmable. Now let's look at how FPGAs can be used in the context of storage functions. So you could have an FPGA be configured by simply uploading a bit stream and making it an encryption accelerator. Now at this point, you could have a lot of data being ingested into the FPGA and we accelerated the encryption engine on the FPGA could accelerate some of these functions, and the data is ingested. Within milliseconds, you could now convert the FPGA into a decryption accelerator, and now you can act on the data using your queries, ad hoc queries on the decrypted data. So you can see you almost double the amount of resources in hardware just simply by uploading a new bit stream. Now, moments later, you could actually convert this FPGA into an analytics accelerator as well. So you can see the FPGA can continue to keep up with the workloads as workloads change. Now let's take a look at one of these workloads. Let's say you have a gzip accelerator that, gzip compression that you want to accelerate, and you actually upload the gzip accelerator into the FPGA. Now, A few months later, if you realize that the Brotli compression engine is actually the right engine for your data, you can come in and you can upload a bit stream that implements a Brotli accelerator, and then you have it. You have a new FPGA, a new hardware that actually does a very different compression engine. And let's say Zipline comes online. It came online in OCP. You can now implement the Zipline accelerator as well on an FPGA. So FPGAs can keep up with the changing workloads and the changing standards as well. Now let's take I want to go through a few examples of how FPGAs can be used in the context of computational storage. So I have two examples from industry. One is from airline industry, and the second one is from the retail industry. And you will see how these industries are using FPGAs and computational storage. So the first one here is an airline data analyst doing queries on a lot of data. This data comes in from 1970s to the present day. There are about 1 billion flight data, hundreds of millions of airport data and plane data, and all of this data is ingested under the Spark framework in a data lake. And now, at this point, when it's ingested, you can actually do ad hoc queries on this data. So this specific example, the data analyst is doing two queries. One has to do with flight delays across the world, and one has to do with flight delays in the sort of the Bay Area. Now you can compare what happens with no acceleration, with no computational storage, with we inserting one SSD, two SSDs, and four SSDs, where the functions, the scanning and filtering functions are pushed down into an FPGA, where the FPGA is doing this acceleration. So here's the data. You can see we almost get linear performance improvement as we add more and more SSDs. So each of the SSDs has computational storage in it. The data is being computed in the FPGA sitting next to the SSD, and you can get near linear performance improvement as you add SSDs. That's the benefit of FPGAs within computational storage. Let's take a look at the second example. Now, in this example, a lot of data is flowing in from individual retail sales terminals into the data center. So there's a lot of data coming in, thousands of terminals sending data into the data center. So given the size of the data, of course, you need to do compression. Otherwise, the storage cost will be high. Now, this compression can be done through either an ASIC or an FPGA. It doesn't matter at this point. You can compress the data. Now, prior to the Christmas shopping season, the main function that you need to do here is decryption, because you need to do decryption of the data so that you can do ad hoc queries. The retail analyst needs to do queries so that they can do pipeline management in terms of inventory management, pipeline management. They need to do some analytics to understand where certain things would go, and so on. But when the shopping season starts, this trickle of data coming in from the retail terminals converts into a flood of data. So as it converts into a flood of data, compression needs spike up. Now, FPGAs in the context of computational storage can keep up with the compression as the data is flowing in over the network. But the CPUs can't, and that's about 20x speed up over CPUs. In fact, if you're not using computational storage or not using FPGAs to keep up with the data, you actually have to switch off the compression to keep up with the data coming in with the CPU. So when you switch off the compression, your storage size, of course, goes up. So let's take a look at the two scenarios, with and without computational storage. Without computational storage, using FPGAs, you need about twice the number of CPUs, and you need about 192 terabytes of storage space. Now, with computational storage, with an FPGA, you can use two FPGA cards doing your computation, doing your compression with a single CPU server, and you can compress the data to about 96 terabytes, and overall, you reduce the number of nodes by 50%, and you reduce the cost by 40%. So that's total cost of ownership. So you got latency, you got performance, you got total cost of ownership. So as you can see, FPGAs can play a very important role in computational storage. They can, like I said, keep up with your workloads. They can get you performance. They can get you total cost of ownership. But there are many ways of deploying computational storage. There are quite a few options. And the SNIA working group right now is focused on defining some of these different architectures. And there are 3 that I'm going to go through briefly with you. So the first one is computational storage drives. Now here, the FPGA accelerator is embedded within the SSD. And the whole SSD with the computational element fits into a standard drive. So as you put in more SSD drives, you get more and more acceleration. So it scales with the number of SSDs. It scales with the amount of data you put in. The other interesting thing about this architecture is that you can have a dedicated link between the FPGA and the SSD, so you can have a lot higher bandwidth than traditionally available to SSDs. Now, the acceleration can also be hidden inside the SSD, so it can be hidden to the application developer. You could be doing compression. The application developer may not even care that there's a compression happening within the SSDs through computational storage. Now, there are 2 partners we work with in this domain. Samsung launched smart SSDs last year, and we are working with them. They have their solution already here at the conference. And ScaleFlux, you heard ScaleFlux talk today, about two talks ago, talk about computational storage. They are also here at the conference showcasing their solution with the Xilinx FPGA within their solution. The next architecture number 2, is computational storage processor. Now here, the FPGA drive fits in the SSD drive itself in a standard slot and communicates with other SSDs. It communicates with other SSDs over PCIe subsystem using PCIe peer-to-peer. Now typically to implement PCIe peer-to-peer, you would actually have to put in a switch, but with AMD processors, now they natively support PCIe peer-to-peer, so you can actually communicate between SSDs using the AMD processors, and you don't need a switch. So here, the advantage is that you are SSD vendor independent. So you can have different SSDs in there. You can slot in your FPGA that does your acceleration, and you can communicate with other SSDs. You can get computational storage through that means. Now, the 2 partners we work with in this architecture is Bitware and Editicom. Again, they are here at the conference showcasing their solutions with computational storage processor being their architecture. The third one is computational storage array. Now here, the FPGA acts as an accelerator in line in between the CPU and the SSD arrays. Again, the advantage is that you're independent of your SSD vendor. You can plug in your accelerator in line in between your SSDs and the CPU. You can also have a dedicated link, if you want, between the FPGA and your SSDs, so you get better bandwidth as well. And the partner that we work with on this architecture is Bitware. So you can see there are many different architectures available to you. There are many options available to you today. But now let's take a look at how we believe the data center architectures will change, how they will evolve, and how computational storage will play a very pivotal role in constructing these new data center architectures. Now, currently, data centers have racks of fixed resources. We have SSDs, they combine SSDs, they combine CPUs and accelerators together, and we have fixed resources, fixed ratios of resources. Now, the advantage here, of course, is there's tighter connectivity between the CPUs and SSDs and storage, but the disadvantage here is that because of the fixed ratio of resources, you can have lots of islands of resources within your servers left unused depending on the size of the workload. Depending on the workload sizes, you may need different types of resources. You may need different numbers of SSDs, different numbers of CPUs, and because there are fixed ratios, the disadvantage is the resource utilization in this architecture. As the growth in data centers as there's a growth in data centers, the data center operators are actually looking to improve resource utilization and to improve total cost of ownership. So one of the architectures you can deploy, and there's a lot of talk in the industry about this architecture, is to make your resources disaggregated. So you disaggregate your resources, so you have banks of SSDs, you have banks of CPUs, and you have banks of accelerators. Now you can compose different resources, and you can configure your resources together over the network through your software, through maybe using Kubernetes, and deploy it for your different workloads. So if you have workload 1, which needs 2 CPUs, 2 SSDs, 2 accelerators, you can compose them together and deploy it for your workload. But if a workload 3 comes along, you may need 3 more CPUs, you may need 3 more accelerators, and you may need 9 more SSDs. You can compose them together and deploy it for that workload as well. Now, this all looks great for resource utilization, right? Great for resource utilization. However, the problem here is that because the composition of these resources happens over the network, you have latency and bandwidth issues. So what you really need is best of both worlds. You need the benefits of latency performance from the first architecture, but you need the resource utilization from the second architecture, the disaggregated architecture. So that's where computational storage comes into play. So just yesterday, in fact, Xilinx announced this Alveo U50 card. We just launched it. And this card is extremely important for the data center architectures that I showed you with. It allows you to do composition of different resources and getting you high resource utilization. Now, this card connects to 100 gigabit Ethernet and implements the NVMe over Fabric protocol in the hardware, in the FPGA, and allows you to do computational storage inside the FPGA. Now, because NVMe over Fabric protocol has been designed for low latency, you can get to the computational storage element, get to that FPGA within microseconds, within a few microseconds more than what it would take to just connect to an SSD that is just a local SSD. So this allows you now to disaggregate resources. So now what you can do is you can move the storage and create banks of SSDs, further away from the CPUs. But because of the computational storage that does NVMe over Fabric and allows you to do computation closer to the SSDs, you can actually get better latency, better performance, and you can get composability as well. Now you can go a step further. You can use FPGAs to go a step further and do network acceleration as well through smart NICs. Now, in the storage conference, it may not be obvious to people, but software developers think about storage and networking just as an I/O. And it may be better to think about what we're doing here in that context. Networking functions also need the same latency and bandwidth requirements. They have the same bandwidth requirements as the storage functions do. So with smart NICs, with FPGAs acting as smart NICs, you can actually do some of these networking functions on the network. So you can do compression and encryption as the data flows in from the network. So you can move those acceleration functions closer to the network. And last but not the least, you can have banks of compute accelerators that can be deployed for larger workloads. You can have workloads such as machine learning inference, video transcoding, all working on banks of accelerators where the amount of compute is much larger than the amount of data. Now you put it all together, you have an architecture that is very composable, disaggregated, very composable, but at the same time gets you latency and performance. You have moved your acceleration functions, your compute functions that are accelerated closer to where they're needed. So they can be closer to compute, they can be closer to networking or storage. Now, in the scenario where your workload is a smaller workload that needs all bytes of data, you can use a few CPUs and a few SSDs with computational storage. in a scenario, in a workload that is much larger, such as machine learning inference and video, you can use much larger pools of resources, such as a bunch of compute accelerators, SSDs, and CPUs. Right? You get best of both worlds. You get the performance and latency, and you get resource utilization as well. All right, so in summary, as you can see, FPGAs are critical for the next generation of data center architectures to build your high-speed data centers. They enable computational storage. They can keep up with your workloads. They can keep up with your standards. You can get the same performance and latency that you would get from an ASIC or ASSP. However, they can be dynamically modified, and you can continue to improve your solution as the new workloads come in. We also showed how you can get up to 5x performance improvement and get to 2x total cost of ownership improvement using FPGAs within the context of computational storage. And finally, Xilinx is leading the way in creating these new data centers that are very composable, that give you high resource utilization, better TCO, as well as low latency and performance. We are bringing distributed adaptive computing to the data center. Okay, so if you want to see computational storage in action, there are, of course, a lot of our partners. You can see almost 14 partners of Xilinx actually showcasing their solutions in booths in the conference. Very proud of all of these partners, working great. And we also have solutions of our own. You should visit our booth, 313. You can see a lot of demos that we are putting in with this Alveo card as well that does computational storage functions. And we also have a website. But if you also are interested in joining the SNIA working group, you can reach out to them as well. So thank you very much, and enjoy the rest of the conference.
Thank you very much.